Let's take a look at some basic probability on a poker hand. The probability of getting this all applies to the same probability rules we use for anything else. The poker setting itself, the actual context, is just a game. It's inconsequential, but it illustrates many of the principles we need to deal with for calculating basic probabilities. So remember, the probability of an event happening is the ratio of the number of successes over the total number. So we have to use combinations to figure out what those two numbers would be when it comes to playing cards and by hand. So before we deal with the S's successes, which is the type of hand you want, no matter what kind of poker hand you're dealing, the N in the equation for the probability is always the same, and that's the how many different ways can you take, say, 5 cards for 5-card poker from a deck of 52. So if I come over here in the spreadsheet to column H, I can see that I want to start with a 52-card deck. I want to come down here and take 5 cards out of that deck. So how many combinations are there? There's 2.6 million possible combinations of cards that come out of a 52-card deck with 5. Notice in the formula line up there, it's the combined function, the combinations function. So in basic probability, we look at permutations and we look at combinations. Excel also has a permutations function. But this basic combination function takes the large D and the small d in rows 4 and 5. So the combinations of out of 52 cards, 5 cards being drawn gives you a number. So it's nice to have the Excel function to do that. You can use the basic formula of r factorial over n minus r factorial. That just takes a lot of extra math. So it's nice to have a function built into Excel for that. Like I said, there's a permutations function that does the same thing if you're looking for permutations. So in terms of our probability of S over N, we know that N is roughly 2.6 million. So just with this spreadsheet empty, what we're already calculating is the probability of getting any one hand out of 2.6 million, and that's the probability in cell I6. So it's a very, very low probability of getting any particular hand. So this kind of spreadsheet you could build yourself quite easily, and if you're working on calculating the probability for anything like this, you would build a spreadsheet very much like this as you go through. So let's take the idea of a desired hand being that we get a pair, say in poker. How would we go about doing that? So basically the way we would calculate that is we're going to do up to 5 combinations, up to 5 cards here. The way the spreadsheet is set up, most of the columns won't get used most of the time, but I could come up with a very, very complex card deck here as I go through. So in getting a pair of cards, what we care about is getting 2 out of the 4 of any particular card. So out of 4 cards for a particular activity, we want to get 2 of them coming out. So out of 4 cards, say 4 threes, there's 6 different ways that you can draw 2 threes from that. So the number of combinations that give you a pair, there are 6 of them for any given value. So the probability of getting that number out of the 6 is quite low, but higher than for any given one hand as we go through. So to complete the formula, when I'm looking at this sum of the values here from 1 to 5, I'm totaling the values here in K. And to make sure I'm calculating my percentage properly, I need to make sure that I'm looking at the same domain as happens in the 52-card deck. So for instance, if I'm going to pick 2 out of 4 cards, I've still only picked 2 cards. So there's 48 cards remaining in the deck, and I need to pick 3 more of them to end up with the number of cards that come out. So while there's only 6 combinations that give me the pair, there are actually, because there are 3 more cards, 17,000 card hands that I could get in 5 cards that come out. I simply won't use cards 3, 4, and 5 because once these numbers total the number of cards in the all, so once these numbers are equal on this other end of the continuum, I know that I've completed filling. I don't need the other columns. So the number of if I want to look for, say, a pair of 2s, there's 103,000 hands that might give me that out of the 2.6 million, so I get a probability of just under 4%. This is a 4% chance of getting any particular pair coming through. Now, if you're a poker player, you know that you could get pairs in a lot of ways. So this is the probability of getting 4% of getting a pair. But what's the probability of getting any pair when I'm playing poker? I have to look at the possible values. So while the pair is a particular set of numbers, there's actually 13 different numbers in the card deck. So I have to show that there are possible values. I could get 6 combinations for each number, but it's actually 13 numbers. So I have to multiply the base probability by the number of ways that it could occur. And what I see is I have a 51% probability when I deal 5 cards out of a deck of cards of getting a pair or better. Notice I say or better. 51% is not the probability, if you're a poker player, of ending up with a pair. It's having a pair or better. Because there are, in fact, hands in poker that include a pair, but that are actually better than a pair. So, for instance, if out of those 17,000 other hands, one of the remaining 3 cards happens to be the same number as I had a pair, what I actually have is 3 of a kind. And that wouldn't be considered a pair in poker. So what I'm calculating here is the probability of getting a pair or better turns out to be about 52%. From that, I would have to subtract the probability of getting, say, 4 of a kind, which also has a pair, or a full house that has a pair, or 3 of a kind that has a pair as I go through. So the actual probability of getting a pair, if you were to work it out, is closer to 40%, not 51%. But the odds of getting a pair or better is about 52%, which is why if you play much poker, you realize that actually getting a pair in your poker hand is not particularly difficult as you go through. So that's one way to use this kind of spreadsheet if you go through. So let's assume we want to do something else. Suppose I want to get a flush. I want to get 5 cards that are all the same hand. So to do that, I know there's 13 cards in each hand. I want to draw 5 cards from the same suit. Now, and get the probability. So the probability of drawing 5 cards out of the same of a particular suit is very, very low. It's way down here at 0.04% as I go through. There's only 1,287 hands that would give me that. But in fact, I have 4 suits in the deck, so I really need to multiply that probability by 4. And what I see is about a 0.2% probability of getting a straight when I deal 5 straight cards. So clearly the probability of getting a straight was much, much lower than the probability of getting a pair, which was between 40 and 50%, depending upon what you include or exclude. So that's why when you play poker, someone who gets a straight easily beats someone that has a pair, because the probability of the hand they're looking at is much lower. The lower the probability of the hand when you're playing cards, the better off you are. So using combinations in the combin function here on this line in the spreadsheet allows me to quickly deduce how many different combinations I would get without having to go through the complicated formula every time. So it pays to have Excel as you go through. And a spreadsheet like this can be used to calculate the relative probability value of virtually any card in a poker game.